So in preparation for this talk, I was thinking about when I took Security Plus probably 8-9 years ago. I don't even remember now. Talks a little bit about cryptography, and a lot of it is just memorizing bit values, memorizing what algorithms might be more secure. But I didn't really understand what any of it really meant, or especially hashing. I felt like I had a difficult time explaining what hashing was. And so I was trying to think where I'm at now compared to where I was then. Who would be the person that would be like the most baseline level of understanding? I thought, well, I don't think my mom really knows cryptography. So for the past month or so, I've been teaching my mom just how modern cryptography works. And some disclaimers I have here: that is not a picture of my mom. So I don't know if you can trust me. She's actually 74. She wanted to be specific about me saying that. And it did not take us half an hour. We probably spent 2 hours talking about Caesar ciphers. So we'll see where we get in 30 minutes. Some goals I have for this presentation is so that you can have a fundamental understanding of cryptography. If people ask what you do, you'll be able to explain it to them at the level of a 5-year-old or to a senior, to another, or noob. One of the things I thought was really cool as I was working with my mom too is just last week she wrote up a handout for me. If anyone want to talk to me after, I can give you a link to a PDF of her explaining her experience with me teaching her cryptography and what she would recommend if you're trying to teach technology to seniors. So there's some common interview questions that hopefully we have time to get over that you'd be able to answer on cryptography. And then I struck out public key infrastructure. I want you to understand that is an important concept in cryptography, but it's something that just it alone would take well over half an hour to get into. But if you're interested in having a better understanding of public key cryptography and the infrastructure, feel free to come talk to me. Okay. So a little bit about me, about my presentation. I've included Easter eggs in some of these slides, as indicated by a picture of an Easter egg. And those slides have something about me that's core to my personality outside of computers. And if you pay attention, you come talk to me afterwards. I've got ties that I'm happy to customize and give out to you. I'm also in the volunteering at the Octopus game, so come check me out. If you want to social engineer me there, you can get some points at that game as well. Yeah. So I've been in IT for a little while now, about 6 years in a security position. Have several certifications. I've done some other stuff as well. Like growing up, I was my dentist's favorite patient, which probably qualifies me to teach on cryptography. But yeah, so certifications that involve cryptography in our industry. CISSP is one of the big ones. There's several domains in that. I have, at one point, achieved 3 of these certifications. So just some things you can look at doing. So when we look at cryptography, first we got to look at and understand what are our goals in security. And if you've been around cyber for a lot, you've seen these. I'm always surprised when I've interviewed people that say they have security experience, and I ask them what the 3 pillars of security are, if they can explain the CIA triad. I'm surprised at how many people don't know what it is. So what the 3 pillars are confidentiality, integrity, and availability. and I'm just reading from the slide at this point. Confidentiality is keeping data information unavailable to those not authorized to view or interact with said data information. So if you have two people communicating A and B, but you don't want C to know anything about that, that's what confidentiality is, keeping it secret from them. Integrity is making sure that the information being transferred is good and that it can be trusted. And availability is, I think, usually the forgotten pillar in security. It's making sure that A can communicate with B. Because if you just took a box, a server, you didn't want anyone to access it, you could throw it in the bottom of the ocean, and then you could say, oh, it's secure, but it's not very available. So cryptography helps us with these. So we look at some historical examples. The Caesar cipher uses substitution. The Caesar cipher, it's a rotational cipher. And substitution means that any character assigned, like you have A in your plain text, you would assign a different letter or character to it, like a C. So that's a very important concept to understand in cryptography. Transposition is not, you don't substitute with a letter, but it moves somewhere else in the message. Those are the two key aspects of cryptography, is changing symbols, substituting them with another, and then moving it somewhere else in the message. The Greek cytel is a historical cipher where they would write a message on a leather band and they would have a rod. They would write the message, they'd wrap the leather band around the rod and write the message, and then someone at the other end would have this, a rod the same size. And if you're looking at these historical ciphers too, most people weren't literate. So you could have a message that keep confidentiality just by writing things down. The Enigma and the Lorenz are examples of mechanical ciphers, where the substitution, like the rotation would change every few rotations. The letters would be substituted with something else. So here's an example of a plain text message. Here is a Caesar cipher of that same message. And then when using transposition, they're all the same letters, but they're moved into different places. So now we're going to get into how the modern cryptography is working, how it's doing substitution and transposition. And to start with that, we look at modern computing. It's based on von Neumann architecture. And that's binary. It uses binaries, ones and zeros. There are other methods of computing that have been tested. There's ternary. But what we use is all down to ones and zeros. And so there's this guy that made this concept known as Boolean algebra. His name is George Boole. And it's just comparison operators of ones and zeros of that binary. So here we have represented the and is an ampersand, or is the pipe, and the exclusive or, which is the most important to cryptography, is represented by 2 ampersand. And if there's one thing that I hope people get out of this talk, is it's how the exclusive or works, that logic. So to understand the AND operator, we have 2 statements here. So 2 is greater than 1 and A equals A. So true, and true is represented as a 1. The OR operator, at least one of the statements has to be true. Here we have the example, okay, 2 is greater than 1. 2 does not equal 3, but at least one of the statements is true, so the result's 1. The exclusive OR is a bit unique. 1 has to be true and 1 has to be false. If both are false, the output will be a 0. If both are true, the output will also be a 0. But if one of the statements is true, only and true. So some great life examples of the exclusive OR that my kids represented for me recently was kind of the opposite game. my kids were arguing about whether it was daytime or nighttime. Can't be both nighttime and daytime. An even better example, so these are switches. Our quantum computing, you kind of have a dimmer switch. With binary computing, it's either the switch is on or off, the light is on or off in a fiber. So this is the example of an exclusive OR that we see every day, and I think it's one of the best examples, is a traffic light. This is a clip, this is a picture taken from the Italian job, and they screw up the traffic lights to be both red and green at the same time. And that's just an accident waiting to happen. It's not a useful exclusive OR because what do? Do you go or do you stop? And so why the exclusive OR is so useful in cryptography is because it's reversible. And so on this slide, I have some representations of bits. Bits are the ones and zeros. Bytes are a collection of 8 bits. And ASCII uses 8 bits. Those 8 bits, the 011, 011, 01, represents a lowercase m in ASCII. That's what we see. Now, if we compare that to an uppercase C, and we do each statement together using the exclusive OR operator, where we have 2 zeros, that's 2 falses, it comes out as a false. 2 trues comes out as a false. And the lowercase m and the uppercase C, when compared, because the computer is doing, it's not doing the substitution with an m to an uppercase C, it's doing the substitution of the bit values compared to each other. And then it comes out with a representation. Those two together is a dot. And so then if we compare the dot to the uppercase C value using that same exclusive OR, it brings us back to the lowercase m. And so that when we're doing cryptography, particularly with the symmetric and asymmetric, we still want someone to be able to get that message in the end, so we have to be able to reverse it. So then if we know if it's easily reversible using this operator, why can't everyone just decrypt it? Why, if they know the values? Well, ultimately it comes down to what is known as the initialization vector or the key. And those can be different, but for high-level understanding purposes, the key is it's where you start in the algorithm. And there's different types of ciphers that will do this in different ways. So, like the electronic code book, the cipher blockchaining, you'll have big blocks of data compared to other big blocks of data, so not just byte values. And those will use things to encrypt the rest of the text. Cipher feedback mode is once you've encrypted, you get this dot, you'll use that dot to encrypt the other text. And so the modern cryptography is doing the substitution and transposition of these bit values, and it's doing it really fast and at a large scale. It's moving things, it's substituting in a lot of ways. The most important thing to know, though, is that the key is the key. So if you're reversing the exclusive OR, if you're going backwards and you don't have the right key, then you'll just create more nonsense, more encryption. So this leads us to what's known as Kirchhoff's principle, which is not to be confused with Chekhov's gun. This is a principle that holds that a crypto system should be secure even if everything about the system except the key is public knowledge. So that's why you can look at AES, you can look at RSA, you can look at SHA algorithm, although SHA is a hashing algorithm. But you can know how these operate, and they're still considered secure. In fact, a lot of ways they're considered more secure because you know how they operate. as long as you don't have that key. So it is of the utmost importance to keep that key secret if you don't want people knowing, if you don't want people getting your message. So if you're telling people where the keys are or the passwords, how to decrypt it, you're not creating a very secure system. And I think it's a really important concept for people to understand that cryptography, when you're encrypting things, if you let people in the door, cryptography is just trying to help prevent people looking in across the wires. But when you let people in the door, when you let people into your systems, it's kind of like watermelon security at that point. If they can get in and decrypt, they can still see everything. So keep your keys hidden. So there's three types of modern cryptography I want to talk about: symmetric, asymmetric, and hashing. So symmetric means that both keys are the same. And this works really fast because it will do that exclusive OR really quickly. But the big problem is if you're communicating over the wires, keeping that key safe, like if I got to get it to you, how's it going to stay safe in transit? And the answer to that, whoa, how'd put that? Okay, there we go, is asymmetric cryptography. Asymmetric cryptography uses a public key and a private key. The public key, and this is where public key infrastructure comes in, use someone's public key to encrypt the message, and then only the person that owns the private key can decrypt it. That's good. And it works on a concept known as modular math, a lot of them. And modular math is like counting around a clock. It's getting the remainders vision. I have some slides later that if you get the slide deck, you can see. We don't have time to go into it. So hashing, symmetric and asymmetric are both helping us provide confidentiality and availability of data. What hashing is most concerned with is the integrity of our data. It's one way, it's non-reversible, it's a fixed length, and it's collision resistant. So that's saying a lot of things. So when I think of hashing, it's like a big wall, and it doesn't use the exclusive OR. It's doing other computations on that to put it into a fixed length. So you see at the bottom, that's a hash value I took of a file. And this is really useful because if anything changes about that file, that hash will be completely different. So that is why it's used in integrity, just to make sure no one will change things. So if you're doing a forensics operation, you always want to take a hash value. You always want to make sure there's a write blocker so that hash value shouldn't change, but you can always compare it. And if things are changing, if you can try to reverse it and figure it out right, you'll get back to that same hash value. And it's also used in passwords. So one of the most important things when people think password security, you really need to be thinking hash security. Because these are what's going to go over the network. And here's some examples. So if I took the password, that's the SHA-256 hash you'll get out of it. And you'll see how all of these are the same length. So that's what it means by fixed length. Password 1, just adding a 1 completely changes that. And then with a lowercase p, you can't predict what these are. And so what people have devised is a way, when people are cracking passwords, they have rainbow tables, they have dictionaries of commonly used passwords, and they have the hash values. So they're just looking to see if the hash value matches that password, and then they can know what your password is. So a protection against that is called assault. Assault will, so the two systems on both sides of an authentication system, one will be able, they know the password and they can compute the hash of it. Assault will add some randomness to it based on the time of day, based on CPU cycles going on. It can be a lot of things that will change that hash value so it will look different every time going over the network. And so when we talk about what it means for hash to be collision resistant, there's an attack known as birthday attacks. The reason they're called birthday attacks is there's a paradox that if there's at least 23 people in a room, there's a greater than 50% chance that 2 of those people share the same birthday. And so when you're looking at hash security, if you have an algorithm that's not collision resistant, then you can have 2 different inputs that are different passwords, but they complete the same hash and they'll still get you into the system. So you don't necessarily need to know the right password, you just need to know the right password that will get you the correct hash that will get you into the system. So we have some common interview questions. How are we on time? Okay. Yes, we can go, if anyone wants to talk to me about doing these common interview questions, happy to go over them. I think we're at time now. Just wanted to quickly say what Chekhov's gun is. Chekhov's gun is a literary principle that if you place a gun in Act 2, it should go off before Act 5. So there you go, there's Chekhov's gun.